Over the next 2 weeks, we'll be studying a topic known as linear programming, and we'll begin with what should feel like a fairly natural jump. Remember, over the last couple of weeks we were studying matrices, but in particular systems of linear equations. So we'll start off this week, we'll start off linear programming by studying systems of linear inequalities. And before we get to systems, let's just study linear inequalities in general. So section 5.1, linear inequalities in two variables. And the first thing we'll do is just make a very simple observation, which is anytime you have a line, that line cuts the plane into two different halves, usually called half planes. So, for example, here I've got the plane, the xy axis. I haven't labeled x and y, but there they are. There's x and y. And I've got this boundary line drawn, and you'll notice that I've got two sides of this boundary line, right? So, below the boundary line, this is usually called the lower half plane, and then above the boundary line we've got the upper half plane. And if you want, I can shade these things. So the lower half plane is everything below this line, and the upper half plane is everything above this line. Okay, so every line does this. Every line cuts the plane into two half planes. One special case with this terminology, though, you'll notice that just about for any line I can talk about what's above and below it, so I've got the lower and upper half planes. But there's one special case where you have vertical lines, and here it wouldn't really make sense to talk about above and below this line because I really only have the left and right hand side. So naturally for vertical lines we just use the terminology, we've got the right half plane, for everything to the right of the line, and to the left of the line we've got the left half plane. So left half plane over here, everything in yellow, and the right half plane is everything over here in red to the right of the line. So just a little bit of special terminology for vertical lines in particular. Every single line cuts the plane into upper and lower half planes, except vertical lines do left and right half planes because it's the only way to sort of name these things in a sensible way. Okay, so fairly simple observation here. Every line divides the plane into two regions known as half planes. Okay, so here's our first example. Find the half planes determined by the linear equation y plus x equals 2. I've underlined equation here because I want to point out that I'm talking about actual equations. We'll do inequalities in just a second, but this is an actual equation because I have an equal sign. And let's see, I want to graph this. I know this is linear, so I know it's a line. Couple of ways I could do this. I could just find any old 2 points on the line. How about the x and y intercepts? That would be easy enough. But how about I just write this in standard form? This is in standard form, sorry, I mean the slope-intercept form. This would be y equals minus x plus 2. Alright, so this would be a straight line cutting through the y-axis at 2, and it has slope minus 1. So something like minus 1. If it cuts through the y-axis at 2, it would also cut through the x-axis at 2. Right? If x is 2, y is 0. So here's our line. How about I just label the point 2 there? Keep going. Alright, there's our line. Y plus x equals 2. And the question was to find the half planes determined by this linear equation. So here we have it. Here we have the upper half plane, and below this line we've got the lower half plane. I don't know if I'm being consistent with my colors here, but just shading one side and shading the other. Okay, suppose though, what does it mean? What does it mean to be on this line? If you're a point on this line, that means your coordinates x and y satisfy this equation, right? So points on the line y plus x equals 2. These are points with coordinates x and y, such that y plus x equals 2. But what if you're not? What if you're not on the line? How about I take, for example, how about I take the origin? How about I take 0 and 0? So what about, say, 0, 0? Well, what if I plug them in? What if I plug in the coordinate 0, 0 into this equation? What do I have? I've got 0 plus 0, well that equals 0, right? How does that relate to 2? 0 is less than 2. Okay? So for this point right here, for 0, 0, for this point I have that is less than 2. And it turns out that for this particular example, any point that you choose in this lower half plane, not just 0, 0, but if you choose any point in this lower half plane, and you plug in the coordinates into y plus x, you will always get something less than 2. Alright? And on the other hand, take anything from the upper half plane. How about I choose this point right here? What coordinates does this have? If this is 0, this is 2, looks like by scaling, that's the point 4, 0. Plug that point into this equation. What do I have? I have 0 plus 4 is 4. That's bigger than 2, right? So also, say 4, 0. What do you get? Well, you get 0 plus 4 equals 4, which is bigger than 2. So that point right there would satisfy an inequality saying y plus x is bigger than 2. And it turns out that if you choose any point from the upper half plane for this example, choose any point at all that you want, when you plug in its coordinates, you'll always get something bigger than 2. Alright, so the observation I'm trying to make is that the points on the line satisfy the equality. The points in either half plane satisfy one of these inequalities. Alright, so hence, for this example, in particular, the line is really the solutions. The line is the solutions to the equality y plus x equals 2. Meanwhile, the lower half plane is solutions to this inequality. Y plus x, what did we get? We plugged in 0, 0, y plus x was less than 2. And it turns out that if any point in a particular half plane satisfies the inequality, then every point in that lower, or that half plane satisfies the inequality. So every single point in the lower half plane, if you plug it into y plus x, you'll get something less than 2. And meanwhile, the upper half plane is solutions to y plus x bigger than 2. Why did I underline for this example? I don't want to leave you with the impression that the lower half plane always gives you the less than and the upper half plane always gives you the greater than. That's not always true, but it is true that one of the half planes gives you one of the inequalities and the other half planes is the graph of the other inequality. So this is what we're going to be looking at in this section. We're going to be looking at linear inequalities like this instead of linear equalities. And the graph, or the solutions to those linear inequalities, will always be one of these half planes determined by the boundary line. So really quickly before we move on, I really want to wrap up that last example. We we had decided that the upper half plane corresponded to x plus y is bigger than 2, and the lower half plane corresponds to x plus y is less than 2. So there's actually 4 different inequalities we'll be working with linear inequalities. You can have a greater than or equals to, less than or equals to, or you can have these strict inequalities, strictly greater than and strictly less than. So the graph in this case, x plus y is greater than or equals to, we already determined that the upper half plane corresponds to bigger than 2, the boundary line corresponds to equals to, so the graph in this case would be the boundary line plus the upper half plane. And in this case, x plus y is less than or equals to, the graph would be the lower half plane plus the boundary line. But in the situation where you're working with strict inequalities, where I've got x plus y is strictly bigger than 2, and my graph is just the upper half plane and doesn't include the boundary line at all, the notation that mathematicians use is they dash this out. So the boundary line becomes dashed to indicate I don't want to include that boundary line in my solution set. It's not part of the graph, I'm just illustrating where the boundary actually is. Alright, so solid line means the boundary line is part of the solution, part of the graph. If you dash it, it means it's not part of the solution set. So similarly, x plus y less than 2 is only the lower half plane, not including the boundary, because the boundary is equality. So once again, dash out that boundary line. So just writing down formally what I just said is the following fact or theorem, if you want, which is the graph of a linear inequality. So here's standard form, ax plus by is bigger than c, or to flip your inequality sign, ax plus by is less than c, is always a half plane, and that half plane determined by the boundary line where you actually have equality, ax plus by equals c. So the question is, how do you determine which one? And so question, how do you determine which half plane? And it turns out in these problems you always do the same thing. So the first thing you want to do is graph the boundary line. Alright, so step 1, graph. Graph the boundary line ax plus by equals c. So as a dashed line, you graph it as a dashed line if we're working with less than or greater than, strictly less than or greater than inequalities, right? Remember, we don't want to include the actual line itself. If we have a strict inequality, the boundary line is really just the boundary and we don't want to include it. So the way we indicate that is we use a dashed line if we have strictly less than or strictly greater than, or if we do want to include it, then we just graph it with a solid line, right? So, or as a solid line, if we're working with an inequality of the form less than or equals to, or greater than or equals to. Because the line is actual equality, since we have less than or equals to, we're allowing equality. The way we indicate that we're including the line in that case is we graph it as a solid line. Just a typical graphical notation mathematicians have come up with over the years. That's usually how we do it. So dashed line means not included, and solid line means it is. And then step 2 is you choose a test point. As we did in the very first example that we did today, choose a test point and plug it in. Alright, so choose a so-called test point from one of the half planes. So choose a test point anywhere not on the line. If that point is a solution, to the inequality, then the graph of the inequality is the half plane from which that test point lives or came from. Alright, so choose a test point anywhere not on the line. If that point is the solution of the inequality, then the graph of the inequality is the half plane containing that point. If it's not a solution, that means the solutions are the other half plane. So if it's not a solution, the graph is the other half plane. So actually a fairly simple process. Someone gives you a linear equality, they say draw the graph, right? Draw the set of all solutions to this equality or inequality. What do? Well, you graph the boundary line. So just change your inequality to an actual equality. That gives you a line, graph it. If you're working with strictly less than or strictly greater than, graph that straight line as a dashed line to indicate that you're not going to include it in your solution set. But if you have a less than or equals to or greater than or equals to, then draw your line as a solid line to indicate it will be part of the solution set. Step 2 is just choose any point. Choose any point not on the line, so coming from one of the two half planes. Choose any test point and plug it in. If that test point is the solution to your original inequality, that half plane containing the point is your solution set, is the graph of the inequality. If it's not a solution, that means points on the other side and the other half plane are solutions. So the other half plane is the graph of the inequality. But I think the easiest way to illustrate this is just with several examples. So let's just proceed. Okay, so here's a linear inequality. Graph 6x minus 3y is bigger than 18. So what do? Step 1, I want to graph the equality. Right, so boundary line. Notice I've got strictly greater than, so I'm going to draw this as a dashed boundary line. Is what? It's 6x minus 3y equals 18. I want to graph this. 2 ways I could do this, I suppose. I could just find 2 points, maybe the x and y intercepts. But how about we just put this in standard form? So what would this be? This would be minus 3y equals minus 6x plus 18. We'll divide both sides by minus 3, so y would be 2x minus 6. All right, there's my boundary line. Y is 2x minus 6. So we'll graph that. 2x minus 6, what is that? That cuts through the y-axis at minus 6. It has slope positive 2. So there's minus 6. Has slope positive 2. That means when x is 3, y is going to be 0. So minus 6 and 3, somewhere around there. This is our boundary line, and I'm going to dash it because we have a strict inequality. So there's my boundary line. This is the boundary line 6x minus 3y equals 18. And what's step 2? Step 2 is choose a test point. I don't know why I've hyphenated this. It's strictly 2 different words. Test point. Somewhere not on the line. So you tend to choose an easy point. You don't want to choose coordinates, minus 72, or sorry, positive 72 and minus 18 or something like that. You'll notice the origin isn't on the line. Anytime that happens, I'm going to choose that as a test point because 0, 0 is very easy. So we'll plug in 0, 0. Test point, 0, 0. Is it a solution to this inequality? Well, we'll plug it in. 6 times 0 minus 3 times 0. What's that equal? 0. Is that bigger than 18? And the answer is no, right? Obviously, it's not. 0 is less than 18. So it's not a solution. 0, 0, not a solution. Which means the upper half plane here is not the graph. It's the other half plane that I want. So this means that the graph is the lower half plane. Sorry about the handwriting there. It's a little hard to write that low on the board. But the graph then is all of this. And that's all there is to it, right? The graph, when I talk about the graph of this linear inequality, I'm talking about the set of all points with coordinates x and y, so that x and y satisfy this equation, or this inequality, I should say. And the set of all points turns out to be everything in this yellow half plane. And not including the boundary line, because I've dashed it out. That's how we indicate not including the boundary line, because the boundary line gives you actual equality. Let's do another one. So I've got 2 more examples on the board here. We'll go through both of these. So the first is graph 4x is greater than or equal to minus 9. And the second one is graph 3x greater than or equal to 2y. And I think these 2 examples should suffice to give us a big enough list of examples to be able to proceed from here. So yeah, let's do this one. 4x greater than or equals to minus 9. So step 1, graph the boundary line. Boundary line. Notice, by the way, I don't have a strict inequality here. I've got greater than or equals, so I'm going to draw this as a solid line, because it will be part of the solution set or part of the graph. And it's just 4x is actually equal to minus 9. So fairly easy to graph this. Let's just isolate x. X would be minus 9/4. Okay. So minus 9/4. Let's move my y-axis a little bit. Okay, so here's x-axis, y-axis. There's the origin. Minus 9/4 somewhere over here. Okay, so there's x equals minus 9/4. So there's my boundary line. I've drawn it as a solid line. This, of course, separates the plane or divides the plane into a right half plane and a left half plane. I just have to decide which one. How do we decide? Choose a test point. Any point not on the line, as we did last time. If I have the origin not on the line, I'm going to choose it because plugging in 0, 0 is usually pretty easy. 0, 0. So my test point is 0, 0. And we just go ahead and plug it into the equation. So if I plug in 0, is 4 times 0, is that bigger than or equal to minus 9? Well, that's asking, is 0 bigger than or equal to minus 9? And the answer is yes. All right, 0 is strictly bigger than negative 9. So that means this point is in the half plane containing all of the solutions. So my graph is the right half plane in this case, including the boundary line. So that's really all there is to it. The graphing linear inequalities is not difficult. It's this 2-step process. Graph the boundary line. We've already studied lines quite a bit, so graphing lines is no problem. Solid or dashed, depending on whether it's a strict inequality or not, and then just choose a point. Choose a point, plug it in, and if it is a solution, then that's in the half plane containing all your solutions. Otherwise, you want the other half plane. But we'll do the second one too. My notes are a little bit out of order here. Yeah, we'll do this other one too. 3x is bigger than or equal to 2y. So step 1, what's our boundary line? Well, that's 3x equals 2y. Let's solve for y. Let's isolate y. This would be y is equal to 3/2 x. By the way, this boundary line will be solid because we have a greater than or equals to. So y equals 3/2 x, what is that? That's got slope 3/2 and y-intercept 0, so somewhere through the origin, something like this. Y equals 3/2 x. Just eyeballing a slope that looks a little bit bigger than 1 there. And we'll choose a test point. Again, I don't know why I keep wanting to hyphenate that. Choose a test point. Any test point not on the line. In the past, in the last two examples, we chose the origin because it wasn't on the line, and 0, 0 is a nice number. Here I can't do that because the origin is on the line. So just choose something else with nice coordinates. How about we choose this point right here, 1, 0. All right, that's not on the line, has simple numbers, so we'll choose 1, 0. And we'll plug it in. So is 3 times 1, is that bigger than or equals to 2 times 0? In other words, is 3 bigger than or equal to 0? And you would say, yes, it is, right? Of course it is. So it is, meaning this point is in the half plane containing all the solutions. So here's our graph. It's the lower half plane in this situation. So I want to do just one more example, but not of this type. Let's go backwards. What if I give you the graph? Can we recover the actual inequality itself? And yeah, we absolutely can. So here's what I'm talking about. Instead of giving you an inequality and asking you to graph it, let's try to go backwards. Here's the graph. All right, so the graph is the upper half plane for this boundary line. The boundary line is a dash, so it's going to be a strict inequality. And the question is, given this graph, can I recover the original inequality? So the answer is yes. What do I need? I really need to know the equation of the boundary line, right? So boundary line. Can we recover this? A couple of ways to do this. We could just take the 2 points that we have on here, plug that into, we should be able to recover the slope from that, right? If I can recover the slope, and I know the y-intercept, then I can just write down the equation of this line in slope-intercept form. So yeah, let's take these 2 points. Let's take these 2 points and recover the slope. Slope equals m. Do you remember how to find the slope? It should be the change in the y-coordinates over the change in the x-coordinates, right? The difference in y over the difference in x. So let's go with this point. This point has coordinates 10, 0. This point has coordinates 0 and 4. So the difference in the y-coordinates of these 2 points would be 0 minus 4. And the difference in the x-coordinates would be 10 minus 0. So our slope is minus 4/10, or simplifying this, minus 2/5. Alright, so there's the slope of this line. And I know the y-intercept is 4, so my boundary line should look like y equals minus 2/5 x plus 4. Now, let's see. There's my boundary line. Suppose I take a point. Suppose I take, let's take 0, 0. So the question is, now that I know my boundary line, is my inequality going to be y is bigger than minus 2/5 x plus 4, or y is less than minus 2/5 x plus 4? Right? Which one are we looking for? Well, I want 0, 0 to not be a solution. I don't like using negatives. How about we choose a point up here? I'm going to choose 5, 0, or 0, 5. 0, 5. I want that to be a solution. let's plug that into both of these and see which one it's actually a solution to. Alright, so we'll plug in 0, 5. What do we get? Is 5 bigger, when I plug in 0, minus 2/5 times 0, so 0 plus 4. Or is 5 less than 0 plus 4? And the answer, of course, is the top one, right? 5 is not less than 4, but 5 is bigger than 4. So this is, in fact, our inequality that gives us this graph. Again, I chose strictly bigger than because we have a dashed line. If it was a solid line, I would have chose bigger than or equals to or less than or equals to. But there's one more thing I should do, which is I'm leaving this sort of in point slope form. For homework in my math lab, it'll specify the form. It'll usually tell you to give this inequality in standard form, as we've done in the last few examples. So let's convert this to standard form really quickly. What does standard form mean? It just means I want this in the form ax plus by is bigger than c. So converting this to standard form. Standard form, what do we have? Just bring the 2/5 x over, so 2/5 x plus y is bigger than 4. And then I need these coefficients a, b, and c to all be integers. So I'm going to multiply both sides by 5. So this would be 2x plus 5y is bigger than 20. And that's typically the form that my math lab is looking for if you come across these questions. It'll specify, it wants it in this form, standard form ax plus by is bigger than c, where a, b, and c are all integers. But that really wraps up this whole section. So the section comes down to just a couple of key facts. If you want to graph an inequality, a linear inequality, the graph is always one of these half planes. It's a half plane that either includes the boundary line or not, depending on whether it's a strict inequality or not. And in order to find the graph, all you have to do is graph the boundary line, choose a test point, not on the line. Plug it in. If that test point is a solution, then that lies in the half plane that is your graph. If it's not a solution, your graph is the other half plane. We'll stop here.